Welcome to Visual Algebra Lecture 2.4, Abelian Groups. Recall that a group is abelian if order doesn't matter, i.e. if AB equals BA for all elements. Every cyclic group is abelian because powers of an element commute with other powers of it. One way to construct new abelian groups is to take direct products of cyclic groups where elements are ordered pairs or k-tuples. Sometimes the direct product of two cyclic groups is also cyclic, and we'll characterize when this happens. We'll state a classification theorem that says that all finitely generated abelian groups have this form. Then we'll see two canonical ways to write all finite groups of a certain order. Formally, a group G is abelian if AB equals BA for all A and B in G. Note that to check that G is abelian, it suffices to only check this condition for all pairs of generators. It's easy to check whether a group is abelian from either its Cayley graph or Cayley table. So this condition that AB equals BA just means that you have a motif like this throughout the table for all pairs of generators. And if this doesn't hold, then you see like red, blue, backwards red, backwards blue is not going to end up where you started. And here's a picture in terms of Cayley tables. Abelian just means that there's always symmetry about this main diagonal. Both of these images are adapted from Nathan Carter's Visual Group Theory book. An easy way to construct finite abelian groups is by taking direct products of cyclic groups. For two groups, A and B, or two sets, the Cartesian product is just the set of ordered pairs of things in A with things in B. The direct product of groups A and B is defined on the underlying set A cross B, and the group operation is done component-wise. So that means if we have ordered pairs A comma B and C comma D, their product AB star CD is just AC comma BD. And here I'm using star for the group operation in the direct product and just plain old multiplication for the operation in the A and B, which are called the factors. Note that the binary operations on A and B can be different. For example, in D4 cross Z4, the operation is multiplication in D4, but addition in Z4. So RF comma 3 star R cubed comma 1, you just take the product of things in the first coordinate, you get RF R cubed. In the second coordinate, you add them, so 1 plus 3, or 3 plus 1, which, if you use the relations, this ends up being R squared F, and 1 plus 3 in Z4 is 0. Note that these elements do not commute, because if you do this in the opposite order, this first coordinate you get R cubed RF, which is equal to F. So hopefully from this example you can see that the direct product A cross B will be abelian if and only if both factors A and B are abelian. The direct product of Zn and Zm consists of a set of ordered pairs, but the binary operation is mod n in the first coordinate and mod m in the second coordinate. In other words, a1 comma b1 plus a2 comma b2 is a1 plus a2 mod n comma b1 plus b2 mod m. Here are two examples. At left we have Z4 cross Z2. As you see Z4, we don't usually arrange it this way, but if we do, we get the Cayley graph, which is rectangular or kind of boxy. And here we have Z2 cross Z2 cross Z2, which we've seen before. As we saw in the early parts of chapter 1, I called this the 3 light switch group, and I'm suppressing the commas and the parentheses. And addition is just component-wise mod 2. The Klein 4 group, V4, is isomorphic to Z2 cross Z2, but I will usually write it as C2 cross C2, if given the choice, because we write V4 multiplicatively, and C2 is my notation for cyclic groups written multiplicatively, whereas Z2 is cyclic groups written additively. Sometimes the direct product of cyclic groups is secretly cyclic. So here is Z3 cross Z2, and if you rearrange or just rewire this Cayley graph, you can write it so it looks like the dihedral group, but notice that both of these arcs, circles, are going in the same direction. And if you number the nodes like this, you put 0 here, 2 here, 4 here. Well, you make the red arrow add 2 and the blue arrow add 3. You can see that this is actually the cyclic group Z6 with a minimal but non-minimum generating set consisting of 2 and 3, like we saw in chapter 1. So here's another Cayley graph of that same group using a minimum generating set of 1. Here's another example. This is Z4 cross Z3, and I claim that 1, 1 is going to generate this whole group. And think about why this is. So 1, 1 is this green arrow or blue, red. So you're going down one row and across one column. And if you keep doing that, down, across, well, down, you wrap around. So down 1, over 1, down 1, over 1, you wrap around, and so forth. How many times will it take to get back to where you started? Well, it's got to be a multiple of the number of rows, which is 3, and a multiple of the number of columns, which is 4. And the least common multiple of those is 12. So think about how this will generalize. We're about to answer that. Is this what you came up with? That Zn cross Zm is cyclic if and only if the GCD of n and m is 1? Let's prove this, and I've included the picture from the previous slide for reference. Let's start with the backwards direction. So let's suppose that the GCD of n and m is 1. And I've basically talked my way through this already. I claim that 1, 1 has order nm. So this is a generator. Has order nm. Now let's think about why this is. The order of 1, 1 is the smallest, so the minimum integer k, positive integer k, such that, well, k comma k is what happens when you add this to itself k times. And this has to be the 0 element in the group. So that's what I mean by the equal sign. So it means k has to be 0 mod n and 0 mod m, which means that k is a multiple of n and m. So that means that n divides k and m divides k. And k is the smallest integer that does this by definition of order, which means that k is the smallest multiple of both n and m. So thus, k equals LCM of n and m. Since they're co-prime, that's nm. Remember, the LCM is n times m divided by the GCD, which in this case is 1. So that finishes that direction. Let's now do the forward direction. Suppose that Zn cross Zm is cyclic of order nm. That means it has an element of order nm. And for convenience, we're going to switch to multiplicative notation and write Cn cross Cm. And let's let that element of order n be a comma b. And the reason why I'm writing things multiplicatively is because that's the only way I can fit this element down here in this circle. There's no way I could do it additively. So if this generates Cn cross Cm, then A generates Cn and B generates Cm. So let's look at a Cayley graph for Cn cross Cm as I have here on the right. So the generators are A comma 1 and 1 comma B. And AB is a generator. That means that if you start here in the upper left and you go down across by one row and one column, then it takes exactly nm times to return to where you started. So, you do this, you're going to wrap around a few times, but since you're increasing your row number by 1 each time, then the order has to be a multiple of the number of rows, and it has to be a multiple, and you're increasing the column number, the column index by 1 each time. The total number of steps has to be a multiple of the number of columns. So that's what I said here, but by definition, this is the least common multiple of n and m. So this is slightly trickier to say, but it's basically the same argument as the converse. So to wrap it up, we can say that if a comma b actually has order nm, that means that the LCM of nm is equal to nm. And remember, the LCM, should maybe write this down, is by definition nm over the GCD of nm. So the only way that these two things are going to be equal is if the GCD is equal to 1. At this point, I want to show you a fact that I wasn't even aware of more than a year ago. I think I got an email out of the blue about it in December 2023, and it's a really neat example to be aware of. So it's that the cycle graph of a group does not need to be unique, and I mean up to graph isomorphism, and I'll explain what I mean by that later. And an example of this can be seen in this group Z5 cross Z2 cross Z2 of order 20. Now, as we just showed, this group is isomorphic to Z10 cross Z2. So we know that there's going to be a 10 cycle. And let's take a 10 cycle. So this is Z10 right here. It's generated by 1, but also by 3, 7, and 9. So these are different Cayley graphs of the same group. Later in this chapter, when we construct semi-direct products, I'll call these things rewirings of that Cayley graph. But for now, there's actually 3 10 cycles, and I'm going to use this format, Z5 cross Z2 cross Z2, and those 10 cycles are generated by 111, 110, and 101. I'll let you verify that if you want. Also, because these are isomorphic, there's a isomorphism between Z5 cross Z2 and Z10, even though we haven't formally defined that. That just means there's a natural pairing between elements in here and elements of Z10. So it means you can construct these graphs, and I encourage you to try, with where the vertices are labeled by ordered pairs, Z10 cross Z2, instead of these triples in Z5 cross Z2 cross Z2. So I think that's a worthwhile exercise. So here are the 2 cycle graphs, and they differ by basically a rewiring of this inner red cycle. And I claim that these graphs are non-isomorphic, and by that I mean fundamentally different. And without defining a graph isomorphism, that just means that I can find a property that one of them has that the other one does not. And now what sort of property would that be? Well, remember in the lecture on the Rubik's Cube, we talked about the diameter of a graph? I claim that these things have different diameters. The diameter is the longest, shortest path between 2 nodes. So if I take a node like 0, 0, 0, and I look at one of these antipodal nodes, the shortest path between these has length 5. So to go from here to 0, 0, 1, there's a lot of ways to do it, but you can't do it in fewer than 5 steps. So 1, 2, 3, 4, 5, for example. And it's not too hard to see that for all other nodes besides these 3, there's a path of distance less than 5. So the maximum is achieved for these antipodal nodes. Now over here, I claim that this node is a distance 4 or fewer from these 3 nodes. So let's see why. So let's go from 0, 0, 0 to 0, 1, 1. So how do we do that? We go down 1, 2, 3. So these are a distance 3 apart. What about 0, 1, 0? So for there, I think we go 1, 2, 3, 4. No, that's not going to work. There we go. 1, 2, 3. And so what about this 2, 0, 0, 1? We do the same thing. I'll go up 1, 2, 3. So actually, these 3 nodes are all distance 3 from here. I think the diameter is 4 because 0, 0, 0 will be a distance 4 from, I'm pretty sure, 4, 0, 0. There's no way to go from here to here in 3 steps. But because the maximum was achieved for these antipodal nodes over here, and these are a distance 3 apart, the diameter of this graph has to be less than 5. So these graphs are definitely non-isomorphic. And so I found this kind of surprising because it seems like to me that the cyclographs are it had seemed to me that were the maximal orbits, and that's well defined. And so cyclographs just putting those things together. But the thing is, there's more than one way to do that. Even if we leave these edges undirected, we're trying not to bias ourselves with picking this generating set versus, or this generator 1 versus its negative. Well, if we rewire, there's a whole nother way to do that. So that seems to be a fairly unexplored aspect of abstract algebra. The aforementioned, well, actually, I did not say it, but there's a discussion on this that I encourage you to look into. It's Math Stack Exchange, and the question ID is 4416395. It's from 2022, and this example does appear. I think it's done by Cayley at Stanford, a CS professor at the University of California. But there's open-ended questions. It was remarked in the discussion that there doesn't seem to be in the entire Math Stack Exchange a previous discussion on this, and the literature is kind of empty on this question. And things that might be worth exploring are what happens, are these the only two you can get? Like, what if you rewire either a blue or a green cycle here? Can you get something different from these two things? I suspect that this is probably it, but I'm not 100% sure. And then also, how does this generalize? Like, is there a systematic way to figure out how many cyclographs there are? I'm not convinced that this is a fully explored problem in mathematics, as simple as it does sound to state. Earlier in this lecture, we showed how to construct new abelian groups from old ones by taking direct products of cyclic groups, or just of abelian groups in general. This theorem, which we are not ready to prove, we won't be till chapter 5 or maybe chapter 6, is saying that every finite abelian group can be constructed like this. So formally, every finite abelian group A is isomorphic to a direct product of cyclic groups. So zk1 cross zk2 up to zkm, where these ki's are natural numbers. Now that's great, but we'd also like to be able to classify these, come up with a complete list of them so we don't have any repeats. So there are, fortunately, 2 canonical ways to organize these factors so we don't double count or miss one. So one way is called by prime powers, where we're going to assume that all of these factors are powers of some prime. So ki equals pi to the di for some prime pi. Another way is called elementary divisors. The name comes from the theory of modules, or vector spaces. And we can assume that each of these indices is a multiple of the next one. So I think we're going to have to see an example for this. And I'm going to look at the groups of order 200, and which factors that as 2 cubed times 5 squared. So there are 6 abelian groups of this order, and I find it easier to write down all of them for any, and with this prime power method. And let me show you why, because we just deal with the primes separately. So groups of order 8, there is either Z8 or Z4 cross Z2 or Z2 cross Z2 cross Z2. That's all we have. Those that have order 25, let me go over here. There's only 2 of them. There's Z25 or there's Z5 cross Z5. Remember, these are not isomorphic because we showed that these are isomorphic if and only if the GCD of 5 and 5 is 1, which it's not. So basically, the prime power method, what we do is we just take all, it says that every finite abelian group of order 200 is the direct product of one of these guys with one of these. And look, there's 3 of these, and there's 3 of these, and here is that list right here. So again, I think I prefer this classification. But if you want to do it by elementary divisors, let me explain by an example really what this is about. So what we can do here is we can take the largest prime power of 2, which is 8, and the largest prime power of 5. Those numbers are relatively prime. So we just put them together. We say, well, this thing is the cyclic group of order 200 because 8 and 25 are co-prime. Over here, we're going to take the largest power of 2. We're going to take the largest power of 5, so that's Z4 and Z25, and that will give us the Z100. And then we say, what's left over? We say, well, now we have Z2 left over and Z2. So this is like a greedy method of just taking largest powers of the primes first. So next, the largest power of 2 is just Z2. The largest power of 5 is 25. So Z2 cross Z25 is Z50. And then we have Z2 and Z2. And then, let's see what color I've not used yet. Then we have Z2 and Z2. For the next one, we take the largest power of 2, that's 8, with the largest power of 5, and 8 times 5 is 40. So Z8 cross Z5 is Z40. Then what's left over? We have a Z5. And then we take the largest power of 2, which is Z4, with the largest power of 5. That gives us Z20. What's left over? The largest power of 2 is 2. The largest power of 5 is 5. We get Z10. And finally, largest power of 2 is 2. Largest power of 5 is 5. That gives us Z10. Largest power of 2 with the largest power of 5 gives us Z10. And then what's left over, the largest power of 2 just gives us Z2. So it's fairly straightforward. It may take a little bit of practice to go from the prime powers to the elementary divisors list. But I find it harder, maybe it's just me, but I find it harder to create the elementary divisors list right from the number n without like missing one or double count. I think usually just missing one. So I should say that this is, there's a lot of ways to write groups like this. These are not the only ways, but these are like sort of 2 canonical ways how you can, if you write these down, you can tell right away that any 2 of these things on this list are non-isomorphic, and any 2 of these things on this list are non-isomorphic. So for example, this group, say right here, is also equal to Z, let's see, let's group them differently, Z50 cross Z4, but, and of course that's isomorphic to this one, so these things are isomorphic. But if you, on exam, I've frequently put a problem like write down a list of all groups of order, something like 200. And if you include this with this list, you're going to be double counting because this is isomorphic to that. So you don't want to include something like this in either list. In general, if you have something like this, there's a whole bunch of ways you can group these factors to get things that do not belong in here. But if you include those, you will be double counting. The previous theorem classified finite abelian groups. There's a classification theorem of finitely generated abelian groups that's very similar. It says that every finitely generated abelian group is isomorphic to a direct product of cyclic groups. Same first sentence as before. But in this case, we allow copies of the integers because we're only assuming that they're finitely generated, not necessarily finite. So that means for some integers n1 up to nm, our group A is isomorphic to k copies of the integers as a direct product, and then zn1 cross zn2 up to znm, where each zn or each ni is a. You can either do the classification here via the prime power method or the elementary divisor method. It does not matter. Again, I prefer the prime power method, so we can assume that each ni is pi to the di. where pi is prime. So in other words, A is isomorphic to we're going to write things multiplicatively, a multiplicative group with presentation, with the following presentation. So the generators of these k copies of Z are just, say, A1 up to AK. Let's say that the generators of these things are R1 up to Rm. Now, each Ri has order Ni, so Ri to the Ni is 1. The AIs have infinite order, so the only relations between them is that they all commute with each other. Similarly, the Ri's all commute with each other. And then the AIs and the RIs commute with each other. I didn't really have to write down this presentation. I don't know how helpful it is to see, or I don't think you'll really be working with it, but it's just worth it to see another way to write something like this and notice why these two things are equivalent. Okay, so what about non-finitely generated abelian groups? They do not break down like this, so they must be kind of exotic or weird, right? Can you think of one? Feel free to pause this lecture. Yeah, just kidding. They're pretty standard. The rational numbers under addition is a abelian group that is not finitely generated. Think about what would generate the rational numbers. So the rational numbers under addition, sometimes we write this just for emphasis, is generated by, well, you need a 1/2, but then you need a 1/3, but then you need a 1/5. You need this for every prime. You need 1/7, and then a 1/11. But even then, you don't have everything because you're not going to get 1/4 from this under addition. So you need a 1/4 and a 1/8. And so there, it's not obvious as to how to even write a minimal generating set for something like this. I'll let you think about it. Well, the real numbers also non-finitely generated, as is the complex numbers. All of these under addition. Now, it's not surprising that these things are not isomorphic to copies of the integers and finite cyclic groups. There's also other groups that, under multiplication, if you remove 0 from these sets, I'm going to write this as with a star here. Some people also write, or some people instead will write like Q. They'll do an X here. Also, as another variation, you can just take the positive versions of the rationals and the reals. Oh, I say you can't take the positive versions of the complex numbers. That doesn't make sense. This is an unordered field, but you can take the positive versions of the rationals and the reals, and those under multiplication, that's a group as well, also not going to be finitely generated. Let's finish this lecture with a quick discussion of other abelian groups. It is clear that the integers are contained in the rationals that are contained in the reals that are contained in the complex numbers, and these are all groups under addition. However, there are many, many more subgroups of the complex numbers than just these. Most, I don't like the word most, some of the following are actually rings, which are additive groups that are closed under multiplication. I'm not saying most because there's infinitely many of them, and most isn't really defined there. We'll study these more later, especially in Chapter 8, which is devoted to rings. One reason why they're not really studied here is because these sets of numbers come endowed with this extra structure of multiplication. And if you study them in the setting of groups, you're ignoring a whole big important part about what makes these sets of numbers interesting. So yeah, they are examples, but they're not particularly interesting examples or really worthwhile doing at this point, other than just being aware that they're out there. One such example that will come up a lot in Chapter 8, actually especially in Chapter 9, is the Gaussian integers. These are complex numbers with integer coordinates. So a plus bi, where a and b are in the integers. So we write this as z square brackets I. We can replace I with a different square root of an integer. So later we'll see z, we say z adjoined root negative m. or positive m. So we'll see things like this and others when we encounter rings of algebraic integers. Turns out that they're more interesting or I think they're more interesting when m is, or when the thing under the square root symbol is negative. Because in that case, well, if this thing under the square root symbol is positive, then this ring just lives on the real axis. Whereas if this is complex, then they also go up here as well. And then there's some tools from complex analysis that we have to analyze these. The set of polynomials in a variable x, we say over the integers, meaning the coefficients are integers, is a group under addition. We write that as z square brackets x. So once again, we study these more in ring theory because they have a multiplicative structure. We can also look at certain subgroups of polynomial rings, like we can take the polynomials of degree less than or equal to n. Polynomials can be defined in multiple variables, like x and y. We say z, or we write z square bracket x and y. We don't really say that. We say the polynomial ring in x and y. So it's a set of all of these monomials, aij times x to the I plus y to the j, well, a set of all sums of monomials. And we only allow finite sums. So we say all but finitely many of these things are 0. And we can also do that over the integers. Oh, sorry, not the integers mod n. So we can do it over zn instead of z. And I say this condition, all but finitely many are 0. We can define, if we drop that condition, so if we drop, so let's say that we cross that out, now we have power series. And we use a double angle bracket to denote that. And again, we'll see this more in chapter 8 and chapter 9. Okay, so that's the end of the lecture. In the next 2 lectures, we will look at groups involving permutations. Specifically, in the next lecture, we'll look at what is a permutation, notations for how to write it, how to compose them, and groups involving permutations, and why every finite group can be written or can be represented in terms of permutations. And then in the following lecture, we'll look at the group of all permutations on an element set called the symmetric group, and the group of all so-called even permutations, which is called the alternating group. These groups are extremely important throughout the class. And there's some really gorgeous Cayley graphs that come up as well. So stay with us.